Good afternoon, everybody. My name is Alex Cross. I'm going to be presenting Analyzing Performance of OpenStack with Grafana Dashboards. So here's my agenda. What is OpenStack? What kind of problems do we have with it? What kind of problems can monitoring help solve there? What is our monitoring stack that we use? Of course, the biggest, the meat and potatoes of this presentation here, dashboards, dashboards, dashboards. I'll also give you some examples of some performance and scale analysis kind of findings that we found using the dashboards. Lastly, whatever could be improved, and if there's time for questions then. So who am I? Alex Cross. Yeah, I know the last name does not exactly look like Cross, but that's how I like it to be pronounced. So, I'm a senior software engineer at Red Hat. I've been there for 4 years now. I'm on the OpenStack Scale and Performance team. I did 2 years on OpenStack so far, and prior to that, I worked on ManageIQ and Red Hat Satellite. And then even before that, I was at Cisco Systems doing system network testing. And I just recently finished my Army National Guard obligation. So what is OpenStack? Show of hands, have you anybody who's used OpenStack? Okay. Anybody who's deployed OpenStack? Okay, cool, even better. So OpenStack is basically cloud operating software. It's for basically creating your own public or private cloud internally. So you'll be able to use OpenStack to launch a bunch of VMs, connect them as a service, and ideally scale them however you need to do. If your app needs more scale, then you'll scale up more VMs. It should all be automated. And because of that, there's a number of services and daemons that work to make that happen. So the key projects within OpenStack are Keystone. That's the identity and authentication project. There's also Nova is the compute one. Neutron is for networking. It used to be called Quantum. Swift for object storage, Cinder for block storage, Glance for image storage. Telemetry used to be called Ceilometer, but Telemetry actually encompasses more than just Ceilometer at this point. So, and then Horizon, and that's not to be confused with Grafana dashboards. That's just their web GUI for OpenStack. So, what are the problems that we encounter with OpenStack? There's many services, many daemons, many projects. There's multiple databases within the database to monitor. There's a messaging bus. There's just a complexity of all these services interacting. And then in any one OpenStack cloud, there could be varying node counts, varying node types, maybe a different layout of putting different services on different nodes or separating services out and separating your control plane out. There's very large configuration files if you ever had to go in and hand edit any of those. The data capture on these test beds, that's always been a problem. Just there's multiple log files, there's different places that you might want to capture information, kind of get that digital exhaust. And of course, if there's an error or a misconfiguration somewhere, sometimes you don't even know about it until way too late. So this to kind of give you a further overview of how complex this mess can be. You can see all the lines drawn on here. Just the number of interactions and different APIs and how things work within OpenStack. You can just see the mess that it is. So this is our monitoring stack. It's pretty easy, probably compared to what you've seen already here. It's not anything complicated or super special. It's basically just collectd we install on each of the nodes. We send over data to, we send our collectd data over to Carbon Graphite. That stores it in Whisper files. Some of the services in OpenStack do have like a metrics logger, and that's pretty sweet, and you can configure that and have that send metrics to statsd, and then statsd can throw our metrics down into Carbon Graphite. And of course, the last part, let's visualize all that via Grafana. So, being on the OpenStack Performance and Scale team, I need to use a number of tools to basically abuse my cloud. So we built an orchestration toolkit called Browbeat, and this uses Ansible, Rally, Shaker, and PerfKit to run various benchmarks against both the control plane as well as inside the data plane. And then we'll even gather some metadata using like an Ansible playbook. We'll just gather all the facts of the host, and then we can also gather a whole bunch of configuration data in there as well. This all happens off of what we call the undercloud. So the type of OpenStack Cloud that I work with is a OOO-based cloud, so that's OpenStack on OpenStack. So to make it even more complicated, I use OpenStack to deploy OpenStack. So what Browbeat will do is it'll combine all those benchmarking results that we'll have with the metadata that we've collected, and it'll also send it to Elasticsearch so we can also visualize those results. As you've seen in a previous talk, you can use Grafana not only to visualize performance data, but you can use it to visualize various benchmarking results, and you can kind of put that on the same pane of glass. So deploying our dashboards, probably the meat and potatoes that we have, one of the things that you guys are probably most interested in is just the dashboards that we have. And those are stored as YAML.j2 files. So a J2 is a Jinja file. It's basically a template that you can apply, that you can manipulate with. So we will take that YAML, and we're going to convert that into graph YAML, and then that gets converted into JSON and sent to Grafana, and that's your actual dashboard there. So the reason why we have all these dashboards stored is obviously, as many of the things that were mentioned in prior talks, consistency of the dashboards, not having to redo the same thing over and over again, and just being able to rapidly deploy dashboards wherever we may need. Because being in a test environment, sometimes I'm allocated nodes, and then sometimes I'm allocated a different set of nodes depending on the testing I'm doing. So I need to be able to generate these dashboards on the fly. I can't go into Grafana and just be messing with the UI. As much as I love to be playing with manipulating individual graphs and individual things, I need to eventually save that off and not have to touch it so I don't forget what kind of tweaks I've made to the specific graphs and whatnot. So all of this is contained within inside of an Ansible playbook. So to get these dashboards up and running, all you have to do is run one playbook, and it'll create the dashboards, and it'll upload them into Grafana. We have other playbooks within Browbeat that allow you to help deploy Grafana, and that's super simple. If it wasn't simple enough already on any type of Rail-based system with just a yum install, we also have playbooks to orchestrate that as well. So how the dashboards are stored, you're probably wondering, why am I using YAML? Well, I only just recently moved to YAML, and that's because I've gotten numerous complaints from the members of my team telling me how they're tired of me submitting 9,000 line Git commits because I was storing the dashboards in Git, like a lot of you guys probably have been doing, or maybe you've moved on to dashboards as code. And it was definitely very unmaintainable. So we had dashboards as JSON, and then JSON.j2s too, because even I got tired of JSON to the point where I would template some of it out and have the vars create a whole giant chunk of the JSON itself. So then that JSON gets converted to YAML, or I'm sorry. So what we've moved to is we've moved to graph YAML, which is actually, you can write your dashboards in a YAML format instead. So what does YAML really give us? It gives us fewer lines, fewer curly braces and quotes. You can put comments inside of the YAML. These are things you can't do in JSON, that it just doesn't look as nice. So some of the advantages that graph YAML gives me, rather than just, why don't I just take the dashboard, convert it to YAML, and have a Ansible filter convert the YAML to JSON, and then use a curl request or the get URI module inside Ansible to send that to Grafana? Well, I can use graph YAML instead. And graph YAML will manage that ID, ref ID, so I don't need to worry about having those being correct inside the dashboard. It'll simplify, it'll reduce some of the lines stored in the YAML, and it does that basically by having some good defaults. So things like the earlier example of saying, hey, if I have all of my legends turned off, I'll have that as a default in there, and then I don't have to define that for every single dashboard. It's a very simple CLI as well. And it can also, you just pass it an API key and the URL, and it will upload all of those. It'll take those YAMLs, convert them to JSON, and upload them to Grafana. So what does Jinja 2 also buy us here? It'll reduce some of the duplication, and we can also take some of those, some of that data, and I can separate into separate files and basically include the files together in a dashboard. So that way I don't have to have, if more than one dashboard displays CPU utilization, I don't have the same CPU chunk of YAML in each of them. So when I did that, I reduced like 40K lines to 6,500 or so lines. So dashboards. So I got 4 different kinds of dashboards. I got static dashboards, templated static, templated general, which are basically the templated static, but I involve a couple more variables in there. And then there's cloud-specific dashboards. So static dashboards, here's some of the static dashboards that I have for OpenStack, like instance count, total memory usage across all of the nodes of a specific node type, so I could sum up my controllers or all my compute nodes and look at what the memory utilization looks there. Probably my coolest looking one is this one, which is the performance comparison. So I'll actually select 2 different clouds and 2 different nodes, and it superimposes them inside of Grafana. And then because there could be a lot of data being displayed at once, I may only select certain items like I did in that top graph there. And you can see like, okay, here's the CPU utilization of the controller node when it's booting machines up, instances every 30 minutes, and I can see how the static CPU utilization on that compute node has gone up. Some of the templated dashboards, we have a Cloud Ceph one, we have a RabbitMQ one, that's the message bus. I have this 3-node performance. I have one for Noki. Noki is one of the sub-projects of Telemetry, and it's one of my larger focuses. So the one on the you can see the 3-node performance one. You'll have CPU, memory, disk, network. We call that the food groups because we're just looking at the 4 main chunks of like resources on your server, see what it looks like. The other dashboard over there is that Noki performance one. I basically put every single metric that I could think of that I use in evaluating the performance of OpenStack's telemetry service called Noki on one single dashboard. So templated general dashboards, these apply to specific node types, such as like the undercloud or an OpenStack controller or Ceph storage or block or object storage and the compute nodes. And so you'd select which node type or which dashboard you'd select which one. If I want it for the undercloud, if I want it for the controller, whichever one, and it has all of the data that you would want to display for that specific one. It basically just changes, the large part it changes really way at the bottom of this dashboard. It's truncated because it's just too large. But the exact processes that would be displayed on that specific, for that specific node type. So cloud-specific are probably one of the other more cool ones. It's basically determined by your Ansible inventory. So however many nodes you have, it'll take those nodes and build a graph of their CPU. So I could have used some sort of templating function inside of Grafana itself, which there is one. But in this case, some of the problems with that is if you have like 150 compute nodes, when I try to draw out 150, it just starts creating a crazy number of querying. So what I do is I batch that. That typically applies to compute nodes because that's usually my heaviest count of node that I'd have. So we have these for memory, disk, network, and logs. So here's an example of the memory. Here's the example of the disk. Disk will have like the percent IO time, IOPS, IO throughput. Network will have packets per second as well as network throughput there. And we can have all of the interfaces graphed on one, or you can select them at the top using the templated vars. For the log, and this is not exactly like a replacement for like an elk stack for analyzing logs. This is merely just having Collectee's tail plugin, tailing and counting the number of info, warn, error logs that are being emitted from those machines. It gives me a very quick point of reference when I deploy a fresh cloud, run some benchmarks, and then I want to scan for when those benchmarks ran. I want to see if any errors occurred on anything. So if I see flat lines there, I'm really happy. If I see errors, then I have to go back and dig it out, figure out what happened there. So let's go through some of those examples that I have. So this is one example, OpenStack Okata versus OpenStack Pike. So Okata is the older release, Pike is the newer one. The next one coming up is Queens. We don't have data for that I could share here. But you can see how, what I did in this test is I scaled up the number of instances on this specific set of hardware and was looking at how OpenStack's telemetry collecting data on those instances was performing. And I'd see if it's getting that backlog down to 0. So in Okata, we had a 20-minute polling interval. It couldn't collect it all until after 5K instances, it struggled to the point where it just blew up. And you could see that it no longer reported those blue and yellow lines, went off the chart. And then the way that it was storing the data basically grew infinitely. Whereas with OpenStack Pike, we saw a much different behavior there. It's too complicated to explain everything right here, right now. But we got to much higher scalability. We got to over 20K instances on the same set of hardware. So here's another example looking at API postings. We had a threaded implementation and a batch implementation. The threaded implementation would spawn a number of Python threads to do a very small slice of work, and it turned out all that work got serialized anyway. And it would be better just to use the same exact WSGI thread we were already in and just create a for loop that would batch all the data in through that one thread right into Ceph. And that was the difference there. It was minutes versus seconds. Here's another example that you could see. Just scanning the graphs, I could find when one of the daemons just basically quit and decided, I'm not doing work anymore. It just went off on the weekend or something. And you could see the backlog on the same number of instances that were running in this cloud. All of a sudden, the backlog's a lot larger, and it's taking a longer time to return. You can see it happens right in the center of that graph there. So here's another example. Your hardware may have a BIOS power setting that could be restricting the performance of that CPU. So if you're not checking for this stuff on your hardware, especially when doing performance testing, it may be difficult to find this type of problem. This problem, the way that I found it, I wasn't even scanning for SMIs, but I did have a plugin. There's a TurboStat plugin that can help you with finding this. But these two compute nodes are running the exact same number of instances on them that are all idle. And at that same period of time, we could see one is consuming a lot more CPU. The one that's consuming a lot more CPU is saving on power, but it's using more of its resources more consumed at that point. And it's more consumed also because SMIs use the CPU. So your actual hardware's BIOS might be stealing your CPU. It's best to have that set into OS control for more deterministic performance. We even use this to find out just odd problems we might have or having to do with the environment that you're deployed in. So in this instance, we have two compute nodes. One has 128 gigs of RAM, and the other one has 64 gigs of RAM. Well, the default scheduling setup for instances favors that compute node that has a lot more available memory. So it just throws all of the instances on that one rather than the other one, and it only slowly starts throwing instances there. So I looked at the instance distribution and saw, wow, there's a huge gap there, and I could see 700 on one compute node when the other ones only had about 50 or 40. And the last example I have here has to do with the Spectre Meltdown patch. So before patching, and then after patching for it, you could see trying to boot 250 instances, I'm sorry, actually 125 instances, not even 250, 125 instances at a certain concurrency with a specific scenario. We can see before patched, fast, after patch, much slower, more than double the time. So what can be improved? Obviously, dashboard storage reuse, there's already been talks about that. Dashboards as code, of course, would be helpful. Queries from different data sources. So we use Graphite. I'd love to be able to interchange my time series database out more easily without having to now go through and figure out every query I need to redo now. Unfortunately, that's not the case right Preserving data, snapshotting is just something that we'd love to have more. There is snapshotting already, but it's just, it is sometimes cumbersome, sometimes it doesn't capture all the data. I'd love to have a more automated way that I could just kind of send an API request to do that. Sometimes the data units, that's been solved with like tagging and whatnot, so that our version of Graphite, we need to move to a newer one. It'd be great to have a standard time series benchmark so that we can compare TSDBs in a more reasonable way. Last one there is metrics interval. We want to collect as something better than 10 seconds. So any questions? I might be out of time, though.
Yeah, we're running a little short on time, but if there was one question, we could take that. Nope? Thanks, Alex.
All right. Thank you, guys.